Okay, so this video is going to talk about complex numbers, and I know when I signed on to Direct last summer and be a Challenge A director, which I was this last year, I was a little terrified because I don't remember talking about complex numbers. And I took calculus through high school, I even had math classes in graduate school, and I don't remember learning about complex numbers. And you might be in the same boat as I am, so I thought on this video we would go through complex numbers and really kind of talk about a bunch of the domains and the things that I wish I had known going into this year of planning for MathMap with my the students in the class and then also with my own daughter. So this is not just going to be for Challenge A directors. This video is for anybody who's going to have a kid in the MathMap and wants to understand the numbers. So let's get started with that. The other thing I also kind of want to point out is I don't feel like in general just the going through the MathMap and kind of reading through it and trying to digest what I could out of the first year was necessarily enough to understand everything I'm going through in this video. I think over time you'd probably get a lot of the information, and definitely on week 27 you cover a little bit more on complex numbers, but I feel like there was a lot of stuff that I was waiting to understand, and it would have been really helpful to know it before the school year had started. So that is the point of this video. So let's start by talking about numbers. So what are numbers? They're just kind of abstract concepts of a quantity. So if I said, give me some numbers, you might say 2, and you might say 5, you could say 7. You could also write these out. So you could write things 2, 5, 7. Ever notice the word 7 has even in it? That's odd. You could also give me tally marks, 2, and you can do 5. You could give Roman numerals. You could do ordinal numbers as well. So you could have first, or you could write that out. You could say second, and you could write that out. What's the Roman numeral number for 0? Trick question. The Romans didn't really use 0, so they don't have a Roman numeral for 0 because they didn't use it. And you're thinking, how could they not use 0? Well, it's actually not that unusual if you think about it. So 0, think about, 0 was probably used like in ancient India, but they weren't really using it in Rome. So 0 is kind of a tough concept. If you thought about, let's say you're talking to a toddler and you're showing them that, you have 2 cookies and I'm going to give you 1, and so that will leave me with 1. This is pretty simple math to help a toddler understand numbers. But how do you say, give me 0 cookies? Well, a toddler probably doesn't understand the concept of 0. You might be able to say, okay, I eat my cookie and you eat your cookie and now they're all gone. So all gone is the same as 0. But 0 is kind of a weird concept. I can't show you 0. I can hand you 2 cookies to give you a manipulative to hold and think about 2, but I can't give you anything to express 0. So 0 is kind of a weird concept, and that's why they don't have it early on in math. Can you imagine doing math and not understanding that 0 is something conceptually that you need? Crazy. Well, so digits in the math map is what they call the digits, the numbers from 0 all the way up to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's great to start with digits because we have 10 digits on our hands. So counting to 10 makes sense for us. That's why we're in a base 10 system. And more about bases in other videos. I'm not going to go through bases today. This will be enough to blow your mind. Okay, so digits is the first thing that they start with in MathMap. So this is kind of like your kindergarten level, your K level, and then starting in first grade level, kind of is the equivalent, is when we talk about naturals. And so these are your natural numbers, your whole numbers that are going from 0 up to 99. And so we call those naturals. And they have a fancy little symbol of an N, and there's kind of like a double bar on part of this N. And so that symbol, that N, when you see that, you know it's representing naturals, which are whole positive numbers. And in that first grade level, they're only going up to 99. So we're keeping it up to two-digit numbers. The negative numbers are going to come along later because negative is a lot harder to understand. So let me go ahead and, oops, sorry, let me erase everything I have here so far. And we're going to talk a little bit about negatives. Okay, so negative numbers, also known as integers, come along later. So if you're a farmer, and I'm a farmer, and I have 5 pigs, and I can think about how I'm going to sell you 2, and so sell 2 pigs, and so I will end up having 3 pigs remaining. That's a pretty easy concept to see. I can see how that works around. But if I'm a farmer, and how do you talk to me about having -6 pigs? Well, that doesn't make any sense. So negative numbers, we think of it and we understand them because we work in negative numbers all the time, right? So negative numbers are debts, are below 0 on the number line. So we start learning about number line when we're pretty young, second, third grade. Oh, throw my 2 in here, sorry. We've been taught the number line since we were young. So we conceptually can understand negative numbers because somebody told us about them and they make sense to us. We've seen how it works conceptually. But to a farmer in the medieval period, a negative number sounds like it's make-believe. It doesn't make any sense unless you're educated. Maybe you would have understood that. But they're not really thinking in terms of negatives. That comes along later also. And integers have their own symbol, and you would think it's a big capital I, but it is not. It's a big Z. Again, you have that double line. And Z, because I guess the German word for numbers is Zahlen. And so the mathematician who decided this is going to stand for numbers used this. And so integers are represented by a Z, this capital Z that looks like this. And so when you see that, I know I'm talking about integers. This is the second or the next domain in the math map. Let me come down here. I actually have the math map on here. So we have talked about digits. That's your 0 through 9. Our naturals are our numbers, whole numbers from 0 to 99. Our integers now have those negative numbers. So I'm going to go from -99 up through 0 and all the way up to +99. Okay, so here are our integers, naturals, and now our next section we're talking about is this Q part right here. And I will clear my board again, and we will talk about our next step here. Okay, so next step, we're kind of moving into fractional stuff. So if I said to give me some fractions or give me a representation of fractions. So here, I have my whole pizza pie here, and I'm going to say, how much is this? Okay, so you as an adult can tell me this pretty easily. You can say this is 1/2. Or you might say it's 50%. Or you could do it as a decimal and say it's 0.5. Or you might even think of it as a ratio and it's 1 to 2. Okay, so over here, just a reminder, we have fraction, percent, decimal, and ratio. Okay, so those are kind of the 4 ways you could write out that fractional amount. So for these fractional numbers, we call these rationals. rationals. And if I look down here, you can see we're going to talk about rationals, but we start, so let's see, this was K, this is kind of like first grade, this is second grade, first, second. So third grade, or kind of equivalent, third grade, only discusses decimals. So I would only consider this fractional amount with the decimal portion right here. So I'm only going to do that in the math map with the problems that I have. So I could have things where I'm dealing with decimals and I'm adding decimal things together and I'm learning where the decimal place needs to go. So when I'm showing you these amounts, that's what the student pages are going to look like in the math map. So third grade-ish equivalent is decimals, where I'm only dealing with decimals. Then in the next level, they add on your fractions. So this is where I can have my 1/2, or I could have it in 0.5, because any of these levels are still using math from the previous levels. It's just adding something else to the complexity. So here in this fourth grade, we are talking about fractions written out as a number divided by a number, or in their decimal format. And then in what's kind of generally fifth grade level, we have all the other rationals. And as you saw up here, the other rationals are including our percent and our ratios. So we're just adding those two other pieces, and then that covers everything that is part of rationals. So what is the symbol for rationals? Well, you might think it should be a big R, which would make sense, but it is not, because we're going to use a big R somewhere else. Instead, it is a Q. And you still have kind of that little bar looking thing on one side of your letter. So that's how I would draw it out. And why would they use a Q instead of, well, they're already using an R somewhere else. We're going to get to that. But why wouldn't they use something else? Well, because the Q in this case is standing for quotient, because these values up here are all some sort of number divided by another number. And that is, of course, the definition of a quotient. So Q stands for rational numbers. And that is the next phase of what the kids are learning. So here you have percents, and then you have ratios. Okay, and so now we get up to kind of sixth grade level, and we are talking about reals. So what is a real number? Let me erase my page here again. Okay, so real numbers include our rational numbers. So it includes rational numbers, includes our rational numbers. Okay, and so as a reminder, those are our fractions, decimals, percents, and ratios. So it includes our rational numbers, which also means it includes those whole numbers, right? Because I could write the number, I can write 1, and I could write it also as 1 divided by 1, or I could write it as 7/7, and that all still gives me the whole number 1. So those natural numbers that we had in the lower levels, there's still ways to represent those as fractional numbers. Okay, so it includes rationals, and of course then that also means it's including all the naturals and the digits before it. Okay, the other thing real numbers include are irrational numbers. So what are irrational numbers? I feel like I've already covered all the numbers. No, the irrational numbers, you actually know some of these. You just maybe didn't know that they're called irrational numbers. These are the things that really cannot be demonstrated in a fractional form. No fractional form. So no fractional format to them. So this is a number like pi. Okay, so when kids are young and we're teaching them to start thinking about pi and using pi, we allow them to use a decimal approximation, and we might say it's 3.14. If you want to get a little more specific, you say it's 3.14159. I don't know any other numbers. That keeps going, right? That goes on forever. It doesn't fully end. It doesn't have a point where it's exactly this decimal amount. And so that's the reason why it cannot be represented in a fractional form, and it is an irrational number. And when you're doing calculations and you're doing a middle school test and you're just trying to get some general circle amount, maybe you can approximate with the decimal 3.14. But if you're a NASA engineer and you're trying to develop rocket ships, and you have a spacecraft and you're trying to launch things, you cannot have an approximation of 3.14 in your math. You need to use pi on everything in your math so that you are considering all of those extended digits where it continues, because you need that more specific information in order to that most detailed information to make sure that your calculations are exact as possible. So in order to keep it exact, you keep it in its symbol format and you don't estimate it over into a fractional format. We do the same thing for phi or phi, which is approximately 1.618. This is the golden ratio, but usually you're using it again in that symbol format. Same with Euler's number. And if you haven't heard much about Euler, you're going to learn all about him this year, or at least you're going to learn about his numbers, which is approximately 2.718. But again, we wouldn't use it that way in our math. We would keep it as the irrational number with just the symbol that we use for it. Okay, so those are irrational numbers. So real numbers are a combination of your rational numbers and your irrational numbers. And the real numbers are what have the abbreviation or the representation with this R. And so you have that R. Oh, and you're seeing all these symbols back on this sheet too. So here's our R. Here was our Q for our quotient or fractional items. Here's the Z for the Zahlen, the numbers with the including integers, and then natural numbers, our whole numbers that are positive. Okay, so now we have moved our way to complex numbers. So complex numbers are let's erase this. We can talk about complex numbers. Okay, so complex numbers are the combination of a real number, we just talked about what those are, the rational and irrational numbers, plus a complex number also has to have an imaginary number. And yes, I know what you're thinking. An imaginary number? Is she crazy? I, which stands for imaginary number. No, an imaginary number is not like some make-believe fairy tale or something. An imaginary number is just poorly named, but it just means it's a different type of number. So the same way that our negative numbers, -2, we conceptually know what -2 is, but I can't show you -2. I can't give you a math manipulative and say this is -2. You just understand that it works. And when you understand negative numbers, well, your whole math knowledge and ability greatly expands because you can use them now in your calculations. Well, imaginary numbers are kind of like that. So imaginary numbers were developed or found because mathematicians were getting to a point where they couldn't continue working math problems when they had negative numbers under the square root. Okay, so what happened is they would get to a number where they'd have a square root of a negative something or another. And I'm just going to say, -32 or something. And then they couldn't calculate any further. Can't calculate. So no more calculations. Can't calculate any further. But they would know that they could continue going. They couldn't mathematically make it work to calculate any further. I think that's confusing how I wrote that. Okay, can't calculate. So it was determined to make the square root of -1 be represented by a symbol, and that symbol is this italic looking I. So I stands for, so this symbol I stands for imaginary number, but it is also equivalent to the square root of -1. And so like up in this problem up here, you could say this is root 32 times I, because I'm now pulling out the square root of the -1. I'm making that equivalent to my I up here, and so then I just have the square root 32 and then I. And now because I have I no longer have a negative under the square root, I can keep calculating that, and then I just leave this I as another variable to it, like I would in other algebra problems, or like how I would have pi, or I could have phi, or one of the other numbers. I just leave it in that format, and then I can keep calculating my other stuff. So this is why they came up with I, which is representing imaginary number. They should have given it a different name because it wouldn't sound like it's a fake thing. But I is equivalent to the square root of -1. Okay. And in the student pages, okay, here we go. This is on the student pages. This is week two, which is when we start talking about number notations. This is the first page of student pages. And early on, this is pretty much the only time you're going to see this. And it is so important, and I can't believe it's just this tiny little spot that you are expected to notice, because virtually everybody misses it, and then it really makes it harder to complete other stuff throughout the year. So it says right here, study the pattern and memorize. Okay, simple little thing. You don't think it's that big of a deal. Wrong. Your student, if they're working through the math map problems, they are going to have problems that have these I's throughout, because it is an imaginary number. They're dealing with a complex number, and if they don't understand these things, or at least know how to sub in stuff, they're going to struggle. So this is what I did for my daughter. We wrote this on a little postcard, and she had it taped to her desk for math all year round. So I is the square root of -1. I squared, you can see how that's the same as I and I, which is the square root of -1 times the square root of -1, and that comes out and balances to -1. So I'm just abbreviating. I'm not writing all of this early stuff because I don't need that all to confuse her. You can see how they got to the math of -1, but I just write it out like this. And I'm going to make these really look like ones so you don't get confused with my I's. Then you have I with an exponent of 3, and that equals -I, and that's right here. I is I times I times I, which is I times I times, or negative root of -1 times root of -1 times root of -1. Two of these become -1, and so it's just -1 times root -1, and so that's -I. Your student doesn't need to understand all of this right now. They might not be able to, but at least write on their card, I with a third exponent equals -I. And then your last one, I with an exponent of 4 equals +1. And you can see how they got that here. They lay it out mathematically, so you can see all the math on how they get to that +1. Again, they don't need to see all of that. I think it's just too confusing. But I would put these 4 things on a postcard, stick it on their desk, and then throughout the year, when they're calculating and they get to something where, it's I squared, they know they can just sub in the number -1, and all of a sudden they went from having up here where they have an I imaginary value, and now they're back in the real world, or the real number line, with a -1. If you want more representation of how you calculate these, I thought it was helpful to understand how these work on the, like on a polar coordinate. So if you're looking at these like in a circular format where it's not really circular, but here's your real number line, and here is your imaginary number line. And these complex numbers are kind of out here where they're either on the real number line, they could be on the imaginary number line, or when you get into certain dimensions, part of them can be real and imaginary. And when it's real plus imaginary, that is when it's a complex number. Okay, so complex number, which, by the way, on the, so complex number was right here, real plus imaginary. So complex number, which is represented with the C, with the little line, is just a real and an imaginary number. And so part of that is in the real number line, part of that is on the imaginary number line. And so like in this case, this point is fully real, this case is fully imaginary, but if I have something that's partially between both of those, it has some component of both of those, I have real and imaginary. And I'll link to my video below that shows more of this, because I think that's a good way for you to understand that. Okay, so something like 4 plus 6i would be a complex number. So this is a real part. This is just the number 4 that we've always known. But this is 6i. It's 6 of the imaginary, so 6i. And that 4 and 6 cannot be added because they're not the same type of term. This is its own type of term that is imaginary, and this is its own type of term that is real. Okay. That also kind of reminds me of the later domains. So right here, as we get into the algebraic stuff, we're talking about adding together terms, right? So we're doing arithmetic, we're adding and subtracting, and we just have different terms, and they might have variables to them. So algebraic expressions, and this is kind of more getting into your 8th grade stuff, you have variables. So algebraic expressions, that's what they start getting into in kind of like complex, or challenge B, which would be kind of 8th grade. So this is the challenge B, 8th grade. So this is going ahead a little bit from the complex stuff. Actually, at the point of complex, they have all the numbers they're going to use. So they're not going to get any new types of numbers. It's just how do they learn how to arrange them and move them together. That's what the algebra is going to cover, but they actually won't have any new numbers that they're learning. So that's kind of a good thing. Monomials are the first of this. So these are polynomials that just have one term. So they're not really polynomials, they just are monomials. They just have one term to them. So something like 2x. 2x is one term. So if I had like terms, I had 2x and 3x. These are both the same types of terms. They have an x to them, but now that they are similar terms, they are the same type of term, I can actually add those together because they are like terms. And those would combine and get me to 5x. Now, when I get into binomial means I have two terms. So two different types of terms. 2x plus 3. That is no longer the same thing that I had above. This was 2x. This was 3x. This 3 is not a like term that can be combined with this 2 because they're not the same thing, because this 2 has an x attached to him. So these are two different types of terms. And then you have, but you may still have to be solving for x somehow. So if I set this with like an equal sign or some sort of inequality symbol, I might have to do something with this, and I could keep solving for it. Polynomials Binomials are where we have multiple terms. So we can have 3 or more terms to it. And this could be solving for multiple things. So an example like this could be something like 6x squared plus 7x plus 2. So this x squared cannot be added to this regular x because they are not the same type of term. And none of those can be added to the 2 because he doesn't even have any variable on him. So if you're solving for this, you'd end up having to kind of FOIL out, which is a higher level math concept. And that's why they're not talking about these things until, high school. So this is kind of like challenge B, where we're starting to see these terms and we might be solving for a variable or combining those together. And then as you get into freshman year or ninth grade or challenge 1, now you were talking about binomials. So now you are taking and solving for stuff. This is probably more specifically algebra. And then you keep increasing the complexity of that in challenge 2 and so on. And that's getting you into polynomials. And it's just the math just gets harder that you're using. So as you continue after polynomials, then they start getting into these expressions. And so you have roots and logs and different things to understand it. And then transcendentals are using more of those irrational numbers. Okay, so there you go. I hope this was useful to you in understanding a little bit more about what all these domains are and what these actually mean without trying to kind of plug through so much of all the other resources available. I think you would eventually get to a lot of this, although I got to say a lot of my knowledge came from outside videos so that I could understand this before I went into my Challenge A year directing. Thanks for watching.